a different idea. So far, we've come up with a formula in Math 171 that describes an object moving up and down. So if you had a point and or a rock and you shot it up in the air, it would go straight up and come straight down based on gravity. But oops, let's just delete that. But if you're shooting an object from like a cannon and giving it a push out into a specific direction, then the motion becomes range. It's getting thrown away from you, not directly above you. So there's a few things that we can do with range, and one of the things we can do is change the angle of the throw. So we can throw it at a very low angle, or we can increase the angle and shoot it up high. And then how far it goes and how high it goes is really determined by two things: the angle of inclination and the velocity of the object. So if you have a very low velocity, it's not going to go very far and it's not going to go very high. If you have a very large velocity, then it's going to go far and it's going to go high, depending on, of course, the angle. So let's play around with a couple of scenarios. And everything here is measured in meters. So going along the y-axis, these are meters, and the x-axis is also meters. So the time is just going to tell us the location of the ball. Alright, so let's set our angle at 34 degrees and give it 15 meters per second velocity. So on the first few seconds, this is what the object is going to do. This is the path it would take. So it would reach a maximum somewhere between around 10 meters away from the cannon and about 6 meters high. And it's happening at 0.8 seconds. That's up here in the corner. And then if we let it keep going, it's going to hit the ground eventually. And it's going to hit the ground at about 24 meters away from the cannon. And it took about 2 seconds to do so. So that's with an angle of 34 degrees and a velocity of 15 meters per second. Oops. So let's change it. Just go backwards here. Change something off to the side here. Okay. Alright, so let's increase the velocity. 22. Hey, why not? Let's increase the angle to be something big. 65 degrees. So here the cannon is now facing a little bit higher, and it's going to shoot up, and it's going to come down someplace over here. So let's see what happens. So it's leaving the cannon. Seems to be going higher than before because we have a higher angle, and it's going much higher than before because of the velocity. So it's reaching a max, probably right about there. So about 20 meters from the cannon, and it's going about 22 meters high. And then if we continue the pattern, it's going to fall about almost 40 meters away from the cannon. And it took 4.3 seconds to get there. So let's go back to the maximum. Somewhere around here. It took about 2 seconds to get to its maximum. So this is the stuff that we need to figure out. How am I coming up with this path first off? And how does changing the angle and which angle is the best to shoot something from to make sure it goes the farthest? So these equations that we're going to come up with are going to be called parametric equations because they're going to self-describe in x and y coordinates separately rather than together like we're used to. So this is kind of the same idea as the cannon example I just went over. So here I have this guy throwing a baseball, and he's throwing it up at an angle of theta, and he's giving it a certain amount of velocity. Now to represent velocity, and you'll learn these later, we get this idea of this length of this line is the velocity of the baseball. And it's going in this direction. So it's going to, go up, and it's going to come down, and it's going to look like, some kind of parabola. All right. So to come up with this equation, we have to kind of break this information into two things that we understand. one thing we understand is the distance off the ground if we throw a ball straight up in the air. This is something we learned in Math 171, the algebra part of pre-calculus. So we have this formula. The distance off the ground is this s of t function, and g represents the gravity due to acceleration. Now g has two different values. I'll write them both down here. So if we're talking about meters, then g is going to be negative 9.8. And if we're talking about feet, then g is going to be 32. So this is what g is for this idea. So half of that would be negative 4.9 for meters and negative 16 for feet. So it depends on how velocity is measured. And this v sub 0 just means the initial velocity, that once the ball leaves his hand, how fast is the ball traveling? And this is how high did he throw the ball from. So if he's like a 6-foot guy, normally he would throw maybe a foot higher, maybe 7 feet high. All right, and again, all these measurements have to match. So the g, the v, and the s, if they're all in meters, they all have to be in meters. And the same thing for feet. So that's one of the formulas that you learned in 171. A formula probably older than that is distance equals rate times time. And this is kind of like if you're driving a car at a constant speed, you can tell how far you've gone depending on how long you've been driving. So using these two ideas, we can break apart this information. So we can talk about, let me switch markers here. We could talk about vertical component of this velocity, because you're throwing it off angle, part of it is still going up and coming down. And then the other part is this horizontal part. How far is it moving forward as you've thrown it? So if we can break it apart into those two things, then we can talk about this being the vertical part of it and this being the horizontal part of it. All right. So the vertical part, if we can find out the initial velocity, this v sub 0, of the baseball based on, his total velocity in off-angled position, not straight up and down, then we should be able to, evaluate both of these formulas. Okay. So let's go back to my main color, main pencil. All right. So if we could just find the velocity, so if the velocity of this thing is, v sub 0, the initial velocity of the baseball going into that angle is, some v sub 0. Now, if it's in meters, it would be meters per second. If it's in feet, it would be in feet per second. So if that's v sub 0, then to find this side, this x, because it's going horizontally, I'll call that x, and we have this angle of the throw, then the x is the adjacent, v sub 0 is the hypotenuse, and that would be cosine. So we could set up, I'll write it over here, cosine of theta is equal to x over v sub 0. And then the x component of the velocity is going to be v sub 0 times cosine of theta. So that would tell me how fast is it moving left to right. Well, in this case, to the right. All right, if we do the same thing for the vertical one, this would be y. And since this is a rectangle, because vertical and horizontal are at right angles, this side also must be y. So the y component of it is going to be opposite over hypotenuse, so that would be sine of theta is equal to y over v sub 0, and therefore y component is going to be v sub 0 sine of theta. So this is the velocity horizontally. This is the velocity vertically. All right. So if this is the vertical velocity, let's start with that one. That's a much more confusing one. If this is the vertical velocity, this v sub 0 sine of theta, then we can plug it in. I'm going to draw an arrow and then erase it. We can plug it in right here into the vertical motion formula. All right, the other thing we need to know is, how tall is this guy and how far is he throwing it from? So let's just call that s sub 0. So this here, right here, is s sub 0, his height of throw. Once the ball, how tall was the ball when he released it? How high off the ground was it? All right, so we can fill in that formula for the y coordinate, because that's what's changing. Y is going up and y is coming down. So we're going to get y is equal to, instead of s of t is equal to, negative 1/2 gt squared plus, and then v sub 0 is going to be this in the vertical direction, so it'll be v sub 0 sine of theta t, and then his height off the ground, whatever it was, is s sub 0. This is a plus sign. All right, so that would be the y formula for how high off the ground this object's going to be after he throws it. The other thing is my horizontal velocity, and that's going to get plugged in right here. Because, distance equals rate times time is just horizontal motion. How far away are you? And this velocity is not changing, it's just the time is. All right? So therefore, x is going to equal my x coordinate, not this x over here. And this is not the y. I really should have called them something else. But the x coordinate of each point on my parabola that I graphed earlier is going to come from v sub 0 cosine theta times t. And this gets known as a parametric equation. And that's how I came up with my graph earlier. I gave it a certain velocity on my slider, and I gave it a certain time, and I set s sub 0 equal to something, and then I made g, in that case, negative 9.8 meters per, or 9.8 meters per second. The negative is already in the formula. And then I just plugged it into a computer and let it graph it. So this is what it means to be a parametric equation. You're changing x and y to be a function of t individually. So we get these coordinates that are generated not just by the x and the y, but by this third variable called t, and that's called a parameter. All right. So let's say we have this word problem. A baseball is thrown at 25 feet per second at an angle of 25 degrees off the horizontal, of course, from 5 feet high. At what time does the ball reach its maximum height? Once you find that, you can also find the maximum height. And how far does the ball go in the air before it hits the ground? All right, so the formula for this thing, I guess we could write it as s of we can write it as kind of like a piecewise function in a way. So the x of t formula is v sub 0 cosine of theta times the time in seconds. And the y coordinate function of t is negative 1/2 gt squared plus v sub 0 sine of theta t plus s sub 0. Well, actually, we should probably call that y sub 0, because we're talking about y on the other side, not s. All right. So if we plug in what we know, then this formula is going to change into v sub 0 is 25 feet per second. So this is v sub 0. And the angle theta is 25 degrees, so this would be theta. And then this 5 feet high over here, that's y sub 0. All right, so we just need to plug these into our formulas and see what gets generated. So v sub 0 is 25. It's going to be cosine of 25 degrees. Shouldn't use 25 twice, but that's okay, times t. And then the y equation is going to become, now here's where you have to be really careful. 25 feet per second and 5 feet high are telling us that g has to equal 32. And the measurement, if you want units for it, is feet per second, also known as feet per square second. All right, so then it'll be negative 1/2 of 32, so that would be negative 16 t squared. V sub 0 is 25 sine of 25 degrees times t, and then the height off the ground was 5. So we have these two equations, one of them being x, this one up here, and the other one being the y coordinate. Okay, so if I want to find out its maximum height, then the height is the y coordinate, not the x. So how do I find the maximum height of y? Well, we do it like we did in 171. We use the formula negative b over 2a. Change colors for a second. So negative b over 2a, so this is b, the whole thing, and of course this is a in our quadratic equation there. So this is going to be negative 25 sine of 25 degrees divided by 2 times negative 16 brings us back to that 32, so negative 32. Then obviously negative over negative is going to make it a positive, so I would take care of that first, because this is supposed to be time, and time can't be negative. All right, so if we type this into a calculator, we get 0.33. So this is approximately 0.33 seconds. So in a third of a second, this thing is going to reach its maximum height. Now, if you want to know what that maximum height is, you take 0.33 seconds and you plug it back into the equation, just for fun. We get 6.7. I think I did that right. So then y at 0.33 would be approximately 6.7 feet. So it's not going very high. 25 feet per second, I guess, isn't that big of a throw. All right, and then it's probably because of the 25-degree angle. The second question says, how far does the ball go in the air before it hits the ground? Well, if you're going to hit the ground, then y of t is going to have to equal 0, because the height off the ground then would be 0. So y of t is equal to 0, and we would have to solve negative 16 t squared plus 25 sine of 25 degrees t plus 5 is equal to 0. That would require the quadratic formula. If I let a equal 25 sine of 25 degrees, this big capital A, then the quadratic formula becomes t equals negative a minus the square root of a squared minus 4 times negative 16 times 5 all over negative 32. And you can use that store feature on your calculator. It'll make your life a lot easier if you just store the number into a and then just do the rest of the formula. Notice one thing, I'm using the minus, not the plus, because the bottom is also negative. Therefore, I'll get a positive answer. So my calculator, I couldn't do it on my fancy write-on one. It was just way too much to type or write in. It's about 0.979 seconds. So almost 1 second. It'll hit the ground. So then the last question is, if that's how long it takes to hit the ground, how far away did it go? Because it says how far does the ball go in the air before it hits the ground. So I need to take the t here, and how far away is this formula? It's the distance horizontally that the object has gone. So here I need to find x of basically 1 second. And we have 25 cosine of 25 degrees times 1, which is cosine of 25, 22.7. So here x would equal 22.7 feet that it has traveled. One thing that's unusual about parametric equations is they're not unique like rectangular equations or polar equations for that matter. So when we have y equals 3x minus 4, that is the equation of a line that has a slope of 3 and a y-intercept of 0, negative 4. And it is the only line that we can write in this way. I mean, we can write it in different organization, but we can't change its apparent qualities. But if we try to write it parametrically, one of the easiest ways to do it is to let x equal the parameter, in this case called t, and then y would equal 3t minus 4. And that's the most elementary way of changing a rectangular equation into a parametric equation. It's also the most trivial. So one cool thing about parametric equations is if we plotted this, we would have to do a table a little bit different than you're used to. You would have a t column. So t usually represents time. Then you would have your x coordinate and your y coordinate. And generally, since t is time, time starts with 0 and then goes positive. So when t is 0, we get 0 and then negative 4 for y. If t is 0 here, then that just becomes negative 4. If we let t equal 1, x is going to equal 1. Y is going to equal negative 1. And then if t is equal to 2, we get x is equal to 2 and y is equal to 6, 2. So I would plot 0, negative 4 here. I would plot 1, negative 1, and then 2, 2. And that, of course, is going to give me a nice line. I'm going to try to draw it as straight as I can. It's not too bad. All right, so that would be our line. And if you look at it, it has a y-intercept of 0, negative 4, and it has a slope of positive 3, up 3 over 1. One of the other things that's true about this line, though, because it's a parameter, we can label each point. This is when t is equal to 0, this is when t is equal to 1, and this is when t is equal to 2. And a second thing that's really important is as we graph these points, this parameterized equation has what's called orientation. So the orientation of this thing is left to right, which is normal for graphs. So let's look at this parametric equation. This one is also a line. I'll give you a heads up on that. So if we do a table, we would do a 3-column table, and t would go here, x would go here, y would go there. And then t, trying to be time, we would let t equal 0. So t is equal to 0, we get x is 2, y is 2. When t is equal to 1, you get 2 minus 1, which is 1. And you get 2 minus 3, which is negative 1. And if you let t equal 2, you're going to get 0 for the x, and 2 minus 6 is negative 4. So if I plot these points, I'm going to get 2, 2, 1, negative 1, 0, negative 4. So I would plot 2, 2 first, plot 1, negative 1, and then 0, negative 4. And if anything, this should look really familiar to the last example. The only difference is I'm starting backwards. This is t equals 0, this is t equals 1, and this is t equals 2. And my line now is going this direction when I draw it. Now, because parametric equations have orientation, I still draw the line, but I have to also indicate its orientation. So this orientation is moving, if you want to think of it this way, right to left. we started on the right-hand side and we're moving towards the left along this line. So it's doing the opposite orientation of a normal function. Functions usually go left to right. So this idea that we can start at the last point on the last graph and end up at the first point on the last graph is kind of a cool idea. And this gives me two parameters of the line 3x minus 4. Here I want to show you how to design a parametric line to start at a specific point and move in a different specific orientation. So generally the way I start these things is I always have them have a left to right orientation, and then it's really easy to flip it around. So we have here, I want to parameterize the line through the point 4, -3 and have a slope of -2 over 3, and it's moving backwards, right to left. So what I usually start off with is recognizing a few things. When you talk about slope, it's change in y over change in x. So if we do this, it would be -2 over 3. And generally, if you're going to make a parametric equation, you separate it. You know your change in y is equal to -2 and your change in x is equal to +3, or the other one. So we're going to play with both of them to see what happens. And then, of course, our coordinate is 4, -3. So we have y is equal to -3 as our start point when x is equal to +4. So I kind of associate the x's with the x's and the y's with the y's. So if I'm going to write my parametric equation, my x-coordinate with a parameter of t is going to be starting at 4, for sure, and then I'm going to add on 3t. Now the 3t represents the change in x. So as t increases, our change in x is going to increase. Then my y parameterization is going to start at -3, and then I'm going to change the y value -2 for every t. So my slope is kind of hidden and separated between the x and the y. All right, so if we do a quick little table of this to see what the orientation is, and also to see if it actually plots the right points, we'll have our t here, our x here, our y here. And let's start off with t equals 0. Now if we have t equal to 0, then we're getting the coordinate for -3, which is great because that's the point I want to start at. And then if I let t equal 1, we're going to get 7 for the x, and we're going to get -5 for the y. And then 2, we're going to get 10 for the x, and we're going to get -4, -7 for the y. So let's see if these coordinates are plotting right to left or left to right. So plug in 4, -3, so 4, 1, 2, 3, 4, -3 is over here. Oh, this one's going to go off my graph paper. Well, I can kind of estimate which way it's going. 7, -5, so I would have to go over 7 and down 5. That would be, further in this direction. So this graph is actually moving left to right. It's not going in the right orientation. Now, to make it go opposite, you have to just go back to the slope, -2/3. I associated the negative with the top, but you don't have to. The negative could also go to the bottom. So if I change the change in y to be +2 and my change in x to be -3, then my other parameterization would be x is equal to 4 minus 3t, and y is equal to -3 plus 2t. Just changing the signs from positive negative to negative positive. So if I do this parameterization of my line, and I do my t is 0, 1, and 2, let's see what happens to my x and y coordinates. All right, so if it's 0, again, we're going to start at 4, -3, which I expect. Then when I let t equal 1, we're going to get 1, and then we're going to get negative 1. So we're actually getting this point. And then if we plug in 2, we're going to get 4 minus 6, which is negative 2. And then if we plug in 2 here, we're going to get negative 3 plus 4, which is 1. So we can plot the point negative 2, 1. See the orientation in this case, let me get rid of my little arrow down here, is going, oops, I just erased a point, is going in this direction as we draw the line through these points. So that would have the correct orientation. And this is the line that goes through 4, negative 3, and it definitely has a slope of negative 2/3. It's just, you would have to go to the second point to see the negative 2, and then the right 3, positive 3. So this is the line, it has the correct orientation. And that's pretty much how you break apart a line, to start at a specific point and go in a specific direction. If I want to parameterize a quadratic like this, and I'll tell you right off the bat, has x-intercepts of 1, 0, 2, 0, y-intercept of 0, 2, has a vertex at, or a vertex at 3/2, comma, negative 1/4. So the easiest way to parameterize almost anything is to write it as x equals t, and then change all the x's to, t and the y part of it. And then this would be a nice parameter. Now, what happens with this parameter is when t is equal to 0, you're going to get y is equal to 2. So the graph is going to start at the y-intercept. So it's going to start at 0, 2. And as t increases, you're going to generate points that are thereafter. So 0, 2 is going to then go to 1, 0. That's going to graph next the point 3/2, negative 1/4. And then you're going to plot the point 2, 0. So it goes through those points and then it goes off to infinity. So your graph would, kind of look like this. It would start at 0, 2, and then it would plot, your x-intercept, the first x-intercept, the vertex, the second x-intercept, and then it would just keep on plotting the points. So your orientation would be this direction, from left to right. All right, the second easiest would be to choose the parameter to be x equals negative t. And then for y is going to become negative t squared minus 3 times negative t plus 2. And then we can kind of simplify that. That's t squared plus 3t plus 2. So when x is equal to negative t, y is going to equal this thing. So if we let t equals 0, I'm going to have to do a table for this one. Set up our 3 columns. So t, x, y. So if t is equal to 0, x is equal to 0, y is equal to 2. So we're starting at 0, 2 again. So when t is equal to 1, we plug it into the x1 and we're going to get negative 1. If we plug t equals 1 into the y equation, we're going to get 1 plus 3, which is 4, plus 2 is 6. And we're going to get the coordinate negative 1, 6. So this graph is going to do the other part of the parabola. It starts at 0, 2, and then it's going to go to negative 1, 6. So now my orientation of the parabola is the missing branch that was here. And therefore the orientation is going the opposite direction. So just by making t a negative t for my parameter, parameterization, then my orientation is flipping. It's going from right to left, left to right, to right to left. All right, so what happens if I change it to be something like x equals t plus 1? Keep it simple. Then y is going to equal t plus 1 all squared minus 3t plus 1 and plus 2. It's almost like a composition of functions. All right, and I can simplify this. This is t squared plus 2t plus 1 minus 3t minus 3 plus 2. So this is t squared minus t, and then the rest of it's gone because 1 plus 2 is 3, 3 minus 3 is 0. So this would be the y version of it. So if I do a table of this one, if I let t equal 0, let's see, we're going to get 1 for x, and we're going to get 0 for y. So now we're starting at 1, 0, which is our first x-intercept. Now if I let t equal 1, we're going to get x is equal to 2, y is equal to 0. All right, and if I let t equal 2, just for the fun of it, we're going to get 3 for x and 4 minus 2, 2 for y. So if I graph this one, we're starting at 1, 0. The next point up is 2, 0. The next point up is 3, 2. And the missing point that we're getting in between, we're going in this direction, is this vertex, which is someplace right here. So our orientation is, left to right, and it's starting at this point, 1, 0, which is kind of cool. So we can get graphs to have a specific look and a specific starting point and a specific orientation. Let's say we want to remove a parameter. In other words, go from a parametric equation back into a regular rectangular equation y of x. So the trick is you're going to solve either x or y for t. Generally, x is easier to solve for t. So we're going to go x equals x equals 3t minus 1, and therefore add 1 to both sides and divide by 3, and we're going to get t is equal to x plus 1 over 3. And then we're going to substitute that into the other equation. So we're going to get out of that y equals something squared minus 4 times something. And that something happens to be x plus 1 all over 3. X plus 1 all over 3. Okay. So we just have to expand this out and see what's going on. So we're going to get y is equal to. This 3 in the bottom for square purposes is kind of messy, so I'm going to square it first and then get it out of the way. So that's 1/9. So it's 1/9 times x plus 1 all squared minus 4/9 times x plus 1. It just makes life a little bit easier. So then this turns into y equals 1/9 of x squared plus 2x plus 1 after we expand it. And then this part over here, I'm going to leave it alone for just 2 seconds. I like it distributing all at once. So y is going to equal 1/9 x squared plus 2/9 x plus 1/9 minus 4/9 x minus 4/9. And then combine like terms. So we're going to get y equals 1/9 x squared minus 2/9 x because of this guy and this guy. And then him and him are going to make negative 3/9, better known as 1/3. So this parametric equation is the exact same thing as the parabola 1/9 x squared plus minus 2/9 x minus 1/3. Kind of a neat way of doing it. Sometimes the algebra gets kind of messy, but it's workable. So let's say we want to parameterize a circle. It sounds complex, but it's really not too bad. The first thing you have to remember is we learned quite a while back now that if we have a unit circle that has a radius of obviously 1, so this is 1, 0 at one of its endpoints, then the coordinate of each one of the points of this circle is based on the angle here, and this would be cosine of theta, sine of theta. The x-coordinate is cosine of theta, the y-coordinate is sine theta. So we've already actually parameterized a circle by the definition of trigonometry. So we can set up that x is equal to cosine of theta, y is equal to, not theta, cosine. So x is equal to cosine of our parameter t, and then y is equal to sine of our parameter t. And we pretty much know what this picture is going to look like orientation-wise. The first point will be here at 1, 0. And then it's going to move counterclockwise until it gets to the point 0, 1. So we know the orientation is counterclockwise. So if we want an orientation to be clockwise, one way to do it would be to change the t's. So let's see what happens. If I want clockwise, then I can parameterize this to be x is equal to cosine of negative t, and y is equal to sine of negative t. Now, if you remember your identities for negative angles and cosine being an even function, that's the same thing as x is equal to cosine of t, and y is equal to negative sine of t. So let's see if this one rotates clockwise. So let's do a little table real quick. And I'm only going to pick major angles because that'll tell us what direction we're going in. So let's see, here's t, here's x, here's y. So my first t is 0, cosine of 0 is 1, sine of 0 is 0, and we get the first coordinate, of course, is 1, 0, which kind of makes sense. If we let t equal pi over 2, then cosine of pi over 2 is 0. Sine of pi over 2 is 1, but there's that negative sign in front here, so this would become 0, negative 1. So right off the bat, we can pretty much tell that this graph is starting at 1, 0, and then as t goes to pi over 2, my next point that gets plotted is this one down here, 0, negative 1. So the orientation of this circle is clockwise, starting at 1, 0 and going around clockwise on our unit circle. So where this one is counterclockwise, our normal setup, cosine of t minus sine of t is going the opposite direction. All right, the main setup though, of course, is going to be a circle of this format. Orientation, you can play with some different methods. One method is what happens if you switch the sine and the cosine. And that's basically just doing an inverse and flipping over the line y equals x. So that also reverses the order of the orientation. Instead of plotting 1, 0 first, you would plot 0, 1 first, and then plot 0, 1, 0 second. So you'd be going in the opposite direction, starting at the top, which is a little weird for drawing a unit circle. All right, so what about if I want to move this circle? What if I want to graph something like, or change a function like x minus 2 all squared plus y plus 3 all squared is equal to 16. Well, the thing you have to notice here is what is the center and what is the radius? Well, the center of this circle is going to be 2, negative 3. Remember, inside parentheses, opposite sign for the numbers. And the radius, remember in this equation, this is r squared equals 16, so the radius is going to equal 4. All right, so I'm going to have a circle that has a different center, and the radius is equal to 4. So if I want to make a radius of 4 based on sine and cosine, that's actually kind of simple. I would say, x is equal to, I'm going to leave a space here in the beginning, 4 cosine of theta. That would increase my amplitude of the cosine out to 4 units away. And the same thing with the sine, I would write it as 4 sine of theta. So if this was my parameter, then this would be a circle centered at the origin with a radius of 4. Now I want to move the x-coordinate 2 units, so I'm going to go 2 plus 4 cosine of theta. And I want to go down 3 for the y-coordinate to start off with. So that would move my center of my circle to 2, negative 3. And then when theta does its little thing, if I was just dealing with cosine theta, sine theta, we would start at 2, negative 3. 1, 2, 3. And then when, I shouldn't call those theta. Those should be t. T for my parameter. You can have a parameter of theta. It doesn't hurt anything. But we'll try to stick with t here. So when t is equal to 0, we're going to get cosine is equal to 1 and sine is equal to 0. So we're going to get the coordinate 2 plus 4, which is 6, which is 4 units in this direction. And then the y-coordinate would be, negative 3, so that would be definitely down negative 3 because sine is 0. So when t is equal to pi over 2, looking straight up, then cosine of pi over 2 is 0, so you're just going to get 2 to the right. Oops, I forgot my plus sign here. And sine is equal to 1, so you're going to go up positive 1. So that would be here. So basically that is 4 units in that direction. So we would be generating a circle around a center of 2, negative 3 with a radius of 4. So that's a quick way of doing a circle's parameterization.